Alright, hell yeah. So we got material mechanics. Now this is impact loading, and this is the video I want to do before I do a proof. You know what I mean? A derivation. So I think this is the way you want to do it. You want to set up an example and even just make it as easy as possible. So, you know what I mean? We got 20 kilograms, and we're dropping this height from a height of 0.1 meters. You know what I mean? Let's switch the problem around. You know what I mean? Let's just make this. I don't know. You know what I mean? How should we make it? I think we should make it 5 meters, and I'll show you why in a second. Should we make this 20 kilograms? Sure. Yeah. So I mean, we're dropping this thing hella now. You know what I mean? And so what we want is when we drop this, it's going to impact the end of this. And sure, it's going to probably stretch the rod, you know what I mean? And I guess that's the first fundamental of material mechanics, is everything is a spring. So, you know what I mean? So even though you have this like metal bar, it's just a really, really stiff spring. Okay, so the first equations, if it's material mechanics, I just have to write all these, you know what I mean? So we do strength is force divided by area. Now they don't call it, they actually call this strength. It's very interesting, but this is stress, and this is in psi. Now this next term they do not call stretch, but I would call this strength, and this stretch. So I guess I'm going to write this strength just so you remember. All right, and then stretch. You know what I mean? Well, what the hell is stretch? Oh yeah. It's this epsilon. You know what I mean? Not very friendly little letter. But what is it? Actually, it's something pretty basic. It's just change in length divided by the total length. Oh, cool. So we got. Well, we'll definitely have to increase this length, obviously. So you know, for maybe our example, we'll just set this whole length at 10 meters. You know what I mean? Hey, that'd be 30 feet. You know, this problem's getting exciting now. You know what I mean? You're just like, whoa. You know, maybe this is going to break the bank. Who knows? You know what I mean? And so we have, that's the stretch. Change in length divided by length. Okay, now, you have to have the equation that links the two. I don't know how you're going to remember this one, but I just think of it as strength is EE. You know what I mean? So we got EE over here. And I would write it like this, EE. Because now this is a constant, you know what I mean? And it would be like writing F equals MA. You know, this would be like writing, well, F is equal to a constant times MA. You know what I mean? So you have something that links force and then mass times acceleration. But with F equals MA, there is no constant, or you could say the constant's 1. But with the strength of a material, you know what I mean? Let's say we have steel. You know what I mean? This is a constant. Cool. And then for steel, what is this? It's 29 million. 29 million psi. And this is in units of psi. And so what are the units on stretch? Well, they're dimensionless. We have like meters divided by meters. So that's going to be dimensionless. Okay, hell yeah. So now, and then you have these three equations, and then the first thing you want to do is like combine them. You know what I mean? So the F divided by A goes into this side. Hell yeah. And then this E stays by itself, but we have change in length divided by length. Change in length divided by length. And now you got to ask yourself, alright, so you want to ask yourself, like, you know what I mean, what do we want to find? You know, maybe we want to find the force. You know what I mean? So the force is just going to be EA. Going to bring the A upstairs. And typically you write it EA, okay? And then I'm just going to divide it by L and then do change in length. And this is probably the first one you want to write, because we have a spring force of a spring is K change in length. And this is the first thing in material mechanics you want to observe, because it's totally spelled out in the fact that, hey, this EA divided by L is your spring constant. And then even right now, I think, and I've not done this yet in other videos, so, you know what I mean, this is pretty cool for you. Hey, you have dimensions of meters right here. Now this is first chapter physics. You mean like, hey, what is the units of the spring constant if we're trying to get newtons? Well, newtons has got to be on top, and we got to cancel out that meters. You know what I mean? So that's kind of the first thing. But then just over here, you know what I mean? Okay, so spring constant is Newton meters. Let's say someone just gave you the spring constant that said, hey, I have a spring constant of Newton meters. No one knows what newtons are, though. So how about and then meters is ridiculous for a spring. No one pushes in a spring a whole meter. You know what I mean? So you know, just so this is really difficult to even come up with a logical hypothetical. But I'm going to do a 4-inch spring, and because I know that's 0.1 meters, pretty damn close. And then I'm going to compress the spring by halfway. Or just so it's a length of 0.5 meter. 0.05 meters. Okay, so we did that. And I'm going to say it took a force, you know what I mean, let's just throw something out. If I'm pushing on it, you know, pushing on a spring, and maybe like 20 pounds. 20 pounds. And then there's a quarter pound is equal to 1 newtons. You know what I mean? Holy Toledo. So if I had 1 pound, that's about 4 newtons. And this isn't a very good conversion at all. So definitely just remember this 4.44. That's pretty easy. And then the other relationship is Mike Tyson. If you can remember 1,000 newtons, which is 1 kilonewton, that's going to be 225 pounds. You know what I mean? Mike Tyson's fighting weight. It's not, even if you Google it, it's pretty close though. But you can just think, oh, he's cutting weight too, so it's 224.8 pounds. Hell yeah, Mike Tyson. And I think he's fighting again. That's pretty cool. Alright, so what the hell are we doing? We were just trying to figure out what 20 pounds was. Okay, so if I have 20 pounds, just multiply by 4.4. So 20 times 4.44, and we get 88.8 newtons. I can live with that. So we got 88.8 newtons. And now what would be our spring constant? You know what I mean? Our spring constant says, I even have to pause the video for this. Alright, hell yeah, I love it when I just have to pause it for a couple seconds. But okay, keep focused. So spring constant is Newton divided by meters. So yeah, I still have no idea. Oh, yeah. And then what did we displace it? So our displacement was 0.05 meters. Cool. And what was our newtons? It was 88.8 newtons. You know what I mean? So we have both of these. We know the newtons, and we know the meters, and we know spring constant is Newton divided by meters. You know what I mean? It's like, so I use this idea that the units are the equation. You're like, okay, well, let's just throw newtons on top, meters on the bottom. So we're going to go 88.8 newtons, and we can double check this one, you know what I mean? So it is, even if you're just trying things, it's all right. And what is that? So we have 88.8 divided by 0.05. Cool, so we get 1,776 newtons per meter. And now you can see, hell yeah. So let's do this. If I had a 2-meter spring, which would be ridiculous, that's the same like spring constant as that spring. You know what I mean? Both the same spring constants. Now we hella changed this length. So is that gonna... No, I mean, I put it this way. This spring is going to look way different than that spring. If we say this spring constant is 1,776 Newton meters, like, you'll just have to think about that one for yourself, but this spring constant is 1,776 newtons. And we can get to that in a second, because you can just imagine, hey, we were talking about this spring, and it's 0.1 meters. Let's say we have the same material and we double the length to 0.2 meters. 0.2 meters. Now, what's the spring constant? Because if I push this you know what I mean, Lucy, like spring, just 0.5 meters. Well, this is half a meter. That's nothing, you know what I mean? So 0.05 meters is just like, no, it's going to be real easy, you know what I mean? So if we took this spring, it's nice and small, made out of metal and stuff, you can imagine that. But then you really just lengthen it out. Oh, hell yeah, we just got just a real easy accordion. And so in this case, I think, and we could run through the equation just so we're set, but it all comes back to this EA divided by L. Even if you have a spring and you don't know the modulus of elasticity, and you don't know the area, which you really don't for a spring, but at least you know the length. And you can say spring constant is EA divided by L. And in this case, we have 1,776 newtons per meter. And we're gonna keep the same material. That's the E part. We're gonna keep the same theoretical area. You know what I mean? Because it's going to be the same material with the same diameter. And but the only thing that we're going to be changing is the length. Okay, so now oh, perfect. And I'm glad I made a huge error. So okay. So we're just gonna say the EA is just 1. You know what I mean? Just you know, it could be. You could have E times A. You could make a spring where it's just 1, and so we're gonna have 1 divided by L is 1,706 newtons per meter. But now what we're gonna do is we're gonna go 1 divided by 2L, and we want to know what the spring constant would be. Oh, whoops. I gotta take a pause. Alright, hell yeah. So I'm happy to take a little break because, you know what I mean, there was that bungee cord problem that got me all the views, you know what I mean? And so it had a spring length of the entire thing and then had a spring constant. But then if you did the problem where you just chopped the bungee cord in half and then just said, hey, that's going to be the change in length of half, you have to use a new spring constant. And if you take that spring constant and chop it in half, hell yeah, your spring constant doubles. So now we know that this spring constant, the bigger the number means the you know what I mean, the more force you're going to have to, you know, the more force the spring can take for a given change in length. I don't know, there's a few ways to look at that. But obviously, you know, stiffer spring, higher spring constant. It's going to require 1,776 newtons to push in this spring. And then if I half it, let's do that. So we're just going to, same material, but then we just half the spring. And I think it's good to get visual of just like, okay, this looks loose. This looks, oh, hell yeah, if that's steel, it's going to be really hard to push. And now if I'm pushing on this, like obviously it's short enough, 0.05 meters, that I could only maybe just go halfway. So, but even so, okay, so 0.025 meters, pushing this spring in a quarter of the distance will be the same as pushing this spring in this half the distance. Okay, because this one, the spring constant is double, so it takes the same amount of force for half the distance as this for the full distance of what we're saying is 0.05 meters. You know what I mean? I guess next time I do springs, I'll try to do 0.2 meters because I don't know. Then your numbers aren't kind of weird. Okay, so there you go. And then if you lengthen this spring, well, now we're going to get a lower number for our spring constant, which means less newtons is required to change the length of the spring. And in this, yes, hell yeah, it's going to be half. But now, from an equation standpoint, let's just do this. Let's go back to this spring is going to be EA divided by L. That is the spring constant. You know what I mean? And let's throw some numbers on it. EA divided by 0.1 meters. Cool. Now this spring is going to be EA divided by, which we can say 2L. you know what I mean, comparatively, if we throw numbers, it might make more sense. This spring is going to be EA divided by 0.2 meters. So what's the representation between these two? If this was a number, this obviously would be that same number divided by 2. Okay, so I think we just kind of proved about 4 different ways, like what the spring constant is, and then how to, if you lengthen the spring, obviously it's going to be loosey. And if you shorten the spring, you cut that spring right in two, you just still have the same amount of steel, and now it's just going to be really hard to push. Cool. And then just in general, the spring constant, newtons per meter. It's totally spelled out in the spring constant number. So if you ever see a spring, and some of them are huge, it's like, hey, 28,000 newtons per meter, that's your spring constant. Well, it looks like you're going to, if you wanted to push in on that thing, you'd have to put 28,000 newtons to go 1 meter. So that's still a spring because, you know, 28,000, if you have a material or a spring that can handle a change in length of 1 meter, you know what I mean? And I would say, like, well, easily you'd have to visualize a spring that was 2 meters long, you know what I mean? And then maybe a change in length of half. So it would go there, and then it would change in length to half. I think that's a good visual representation for springs. But now this would say that you'd have to put 28,000 pounds, and that seems like a lot. The strength of steel, a good one to remember, I just used the 58,000 pounds 58,000 pounds per 1 inch of surface area of steel. Whether you're putting it in tension or compression is the same. So you could hang 28,000 pounds. No one knows what 28,000 pounds is, but 58,000 is pretty close to like a semi. That's, you know what I mean. Like I think 40,000 pounds is like the semi cab empty trailer, maybe. And then the full weight of a semi is usually up to 80,000 pounds. So you know what I mean. Somewhere in loading a semi, you get to this range. Man, I don't know. Maybe just something not as heavy as a semi, but you can imagine that if you you know what I mean, put that on a scale. So if this is your, you know, driving, and then that scale would go down 1 meter. I mean, if you just had a you know, whatever, you know what I mean. So let's see. But with, and then this is the thing, is people don't really understand material mechanics problems because your changes in length are so tiny. You know what I mean? Let's say we do have 10 meters of steel. You have to remember this number, 0.002. Because just like strength has a max number, I can just spout it out. This stretch has a max number for steel, and it's 0.002. It's a really pretty accurate number, and you can't go wrong with it. And if you can't remember that, just think 0.2%. That's still a sucky number to memorize. But if you think percentage, you're like, oh, okay, a change in length of 0.2%. That's going to be the max max change. Well, I don't know. I don't want to confuse myself, but it is a ratio of the change in length divided by the total length. So if I had a 1 meter total length, I could, and then we'll do this. If I had 1,000 millimeters, that is 1 meter, and then what would be my change in max change in length? Well, just visually, it's going to be 2 millimeters. And do we get this number? If we take the change in length of 2 millimeters divided by 1,000. Anytime you divide by just like a number that's like 10 to the 3, you know what I mean, with 3 zeros and a 1 right here, you just take where your decimal is right here and just go 1, 2, 3, and then put a couple zeros. So hell yeah, so that's 0.002, and that's going to be representative. 2 millimeters of change in length for 1,000 millimeters. Now I think what happens in material mechanics is people don't treat this as a legit equation where you have three things. You know what I mean? Going back to kinematics, and this problem will involve kinematics. If I have acceleration, I know that's change in velocity, change in time. And if I'm talking about average acceleration, this is a legit equation. If acceleration is constant over a given change in time, you know, let's say gravity and stuff, this is an equation with three things. And that means you can rearrange this equation three different ways. You can say change in velocity is acceleration, change in time, and then you can say change in time is equal to change in velocity divided by acceleration. You know what I mean? And so the same thing here with this strain equation, or this stretch equation, however you want to say it. Because we have, let's write the three ways. Strain, or stretch, is change in length divided by length. And this is where it's like, I call it the stretch equation, where like your change in length is kind of your visual stretching, but it's a ratio, you know what I mean? So, but just in general, I think calling this strain it sounds too much like stress. People don't understand this equation for what it is. It's very actually simple, and I think just calling it strain and then putting in the symbol epsilon, which is also a bizarre symbol. Not too many properties get the little symbol epsilon. And I think it just gets overall confusing. So here we go. So we have the strain is the stretch divided by length. Cool. And then let's say we wanted to find the length. If we know the stretch, change in length divided by the strain, hey, we could figure out the length, I guess. And then what's the other one? We could figure out change in length is strain times length. All right, hell yeah. And I don't know if we're going to do that right now. And then the other thing with, like, hey, so this property of strength, this is such an important thing. Every material mechanics, video that I do is like, I'm going to go over the basics. Because if you don't take this course, if you don't do material mechanics problems for more than a year, you're just like, oh, damn it, what were the basics? Because here's one. I said this strength was 58,000 psi. Cool, but that's a max strength. And you could label it like this, max. You could label it like this, maybe like the yield, or maybe it's the ultimate. Maybe it's just the tensile strength. So this definitely gets a subscript. But let's say we don't put very much force at all. We just put 1,000 pounds. You know what I mean? But we have something that can take 58,000 pounds. Well, now that's just the psi that and we're still dealing with like a 1 square inch steel. So now our force is 1,000 pounds divided by 1 square inch. So we have 1,000 pounds per square inch. So we're only getting 1,000 psi, and we're nowhere near this top end. And that's the same thing for strain. Is like, hey, yeah, if we have a 1 meter length of steel, we can only stretch it 2 millimeters before, you know what I mean? Like in structural world, if you're actually designing it and you stretch it more than 2 millimeters, hey, maybe people could die. But steel does go plastic and it stretches, you know what I mean? So if you're just out there welding in the shop and stuff, hey, you can do crazy things and bend it with steel and still maintain some sort of structural integrity. But just from the building of things, you know what I mean? The second you're starting to pull on this, like this would be a classic example. If you impact this where you go past the 2 millimeters of change in length, it might not be a big deal because you're only putting that force on for maybe a short period of time, and that extra change in length can absorb the energy. Where compared to if you have just an overloaded bridge that that's like ready to collapse, the second you get past the point where things, this 2 millimeters for a 1 meter bar, then the second you get into that range where you put more force, or your change in length is more than 2 millimeters, well, it's just going to keep stretching and then break with a catastrophic failure. There's probably nothing. The second it stretches and deforms, there's probably nothing to other things to take the load. All right, hell yeah. So So what we're going over is the idea that, this is the max stretch. But I would always, whatever problem you're doing, I would always get the high end, your max stretch and your max change in length. Because even right here, let's say we do have 2 meters, I can just say, whoa, hey, I know for every meter it's going to stretch 2 millimeters, and so I know my max stretch, my max change in length can only be 4 millimeters, or 0.004 meters. Okay, now let's use an equation to get there. So that's where that tangent was going, because it is good to maybe throw max on these for your first time around, because this is going to be your check on reality. But obviously, if you observe that your change in length is only 2 millimeters and you have a 2 meter bar, well, now your strain is going to be, well, let's do it. It's going to be 2 millimeters divided by 2,000 millimeters for your length. And now you have a strain of 0.001. And that's half of the max. And no duh, because we said at 2 millimeters, a material mechanics thing is just like, well, I can easily say how much this can stretch. That's really cool. Just like if I know the surface area of this, and so we're going to have diameter, the area of a circular, bar is going to be pi r squared. Hell yeah. And so we're going to have an area. But let's get this to inches, since, I always try to do material mechanics problems in pounds and inches. In America, that's the only thing you're going to be familiar with, because your strains are going to be in pascals, which is just a whole nother level of confusion, because just like a PSI, we can all know what the hell a PSI is. 1 pound, but it's only over 1 square inch. That's actually quite a bit of weight over 1 square inch. But steel, even if you have a cubic inch of steel, that's only going to be 0.29, 0.3. So you would have to have over 3 inch. You would have to have a thing of steel that was 1 inch by 1 inch, and it would have to be like 3.25 inches high. And that would generate. That'd pretty damn heavy. But what we're saying is that's just 1 pound of steel. So 1 cubic inch of steel is only 1/3 of a pound, let's say, and you have to have about 3 of those inches, or 3 inch by 1 inch. But it's just amazing. You get steel. Steel has a density of 7, and so it's just fascinating that you could be holding a whole pint glass, which is kind of large, or just like a 1 inch by 1 inch, which isn't very big, and then just by 3 inches. And that chunk of steel is going to weigh 7 times more. It kind of relatively. Obviously, a pint glass is made out of glass, and that's got a density of a 2. Kind of like rock. But anyway, all right. So what's a pascal? A pascal is going to be a whole meter. It's a huge area. A meter is a massive area, and then you're only putting 1 newton on, which is a 1/4 pound. And literally, I do the newspaper analogy. If you got Wall Street Journal, even the Wall Street Journal isn't even a meter. You would have to cut like a few pages to get a whole meter of surface area of Wall Street Journal. And then you would have to do that twice. You'd have to get 2 layers of that. If you did 2 layers of that, you'll have a 1/4 pound of newspaper, and it'll cover a surface area of 1 meter. So it's just like, oh yeah, it's like less than, your sheets. You know what I mean? So anyway, so yeah, a pascal is just very small pressure. So that's why we convert. So 15, and then the conversion is 25.4 millimeters is equal to 1 inch. Cool. And then I would never write it like that. You want to use factor label. So if we have 15 millimeters up top, we want to put 25.4 millimeters downstairs and then 1 inch upstairs. Because now, when we convert 15 millimeters to inches, hell yeah, millimeters cancel, and we got 15 divided by 25.4. And obviously, you can do that in your head. If I had 25 millimeters is 1 inch, but I only have like half that, or like 13, well, obviously, I have about ½ inch. Cool. So I'm going to use that, and I'm going to square it. This is the diameter. This is diameter. You know what I mean? So we have about a ½ inch diameter divided by 2. We got 0.3 for our radius. We're going to square that. And now we're going to times it by pi. I guess the better equation for area for material mechanics, because you use diameter a lot, is definitely just pi d squared divided by 4. Pi divided by 4 times d squared. So we can do that just to make sure we got a check on reality. There's our diameter, square it, times pi divided by 4. And, whoa. Alright, so 15 divided by 25.4 is our diameter. And we're going to square it times pi divided by 4. And we're going to store that as alpha area. We're going to store this as alpha diameter divided by 2, stored as the radius. So now we have 2 pi r squared, and we get that same... Why am I losing my mind? Alright, alpha r, alpha d. If this is the diameter, we're going to square it times pi divided by 4. That's the area. So which one is wrong? Which one of these is wrong? You know what I mean? Pi r squared. Pi r squared is the area. So we'd have alpha d divided by 2 squared times pi. And okay, hell yeah. So we get the area. I don't know what mistake I was making, but now we have an area of 0.27 inches squared. Okay, and now here's our first check on reality. That's fairly easy. Like obviously, if this had a hella diameter and it had a surface area of 1 inch squared, just always use that as your reference. Oh, this thing could hold 58,000 pounds, just right there, 58,000. But it doesn't. If it had a half of an inch, you know what I mean, it would be 58 divided by 2. That's 29. But it doesn't even have that. If it had a quarter, it'd be divided by 2. It'd be 14.5. It'd be 14,500 pounds. So we're pretty close to that. So we have alpha A times 58,000. And so these are the things that you don't even want to use the equations for. You could, because we do have that. And so here's the other equation, and let's do that one 3 ways. So we have strength is force divided by area. Let's solve for force. That's going to be strength times area. And let's solve for area. That's going to be force divided by strength. Cool. So what we just used is strength, 58,000, times alpha area. Cool. And it's just, that's going to be the fundamental understanding probably from this video, kind of one of the huge take-home points, is if you have one equation, you have 3. You know what I mean? I can't reiterate that enough, because it's just, you'll just baffle yourself of like, oh, okay, I have one equation, now where do I go from there? So always, if you have one equation, you know what I mean, hey, you got 3. Even here, when you put all these together, holy hell, you know, you not only have 5 equations, because you can put one letter over here equal to all the other letters, but you have more than that, because force over area is an equation. That's like, so that's like your 6th equation. Then you could solve for, you know what I mean? So it's just fascinating how you can solve for different things. Even yeah, in this case, yeah, you have multiple equations you can use. Alright, hell yeah. So, yeah, it's just so cool that you don't even need the equations to kind of set up a problem and be like, hey, we got a 1/4 inch, you know what I mean, it's going to be 58,000 divided by 4, you know what I mean, so yeah, alpha A times 58,000. Yeah, so, you know, we can put, on this thing, we can put exactly 15,886. Now, this is an exact answer, let's say. So that's how many pounds of force you can put before what happens? Before you're maxed out on the change in length. And now we have to talk about this. This is a spring where if you get to that max, it really can't take any more. It's going to start to lengthen. Now it can take, because you do have some sort of strain hardening, and the physics behind that is maybe you don't have a perfect structure, but then when you actually stretch it, all the voids will like kind of collapse together, and then like the molecules will get more stringy and very long lines. And so you get a strain hardening, kind of just like a better structure as you're pulling it. And then you actually get more strength out of it. And it can go a little bit higher. But who cares? You don't want to kill people. You don't take it to that point. Because after that point, you're going to have permanent elongation. So even with our setup, we can change its length by 4 millimeters. Let's say I got a little gauge down here, and I put whatever force, who cares, but then I change its length by 6 millimeters. 2 millimeters passed. And then what happens when I let go? Well, it goes back, it's permanently stretched, but only by 2 millimeters. It will go back, it will rebound 4 millimeters. It'll always rebound 4 millimeters as long as it's not broken, as long as this thing is still in 2 pieces. And I find that very fascinating. You know what I mean? It'll still rebound. Now, is that true? I have to think about that. Yeah, that's totally true. So let's grab a fresh sheet of paper, and we can kind of talk about that, because that's the thing that I'd never really like to talk about, is like the stress-strain diagram, but it is probably fundamentally important. It's just kind of bizarre, and you really don't, I don't know, it's like you don't need to talk about it more than just this part. Like, don't kill people. Don't go past that. This is called the strength yield, and this is when you do pass that 4 millimeters. And then you permanently elongate it once you take the force off. You know what I mean? And then so basically, if you just want to make it a simple concept, even though it does strengthen, goes up here, comes back down, and then breaks, this distance right here, you know, if you actually did it to scale, it would be a totally vertical line. You couldn't even tell that it was a slight angle, and then you would have this, you know what I mean? Because this would be your 2 millimeters. So visually, there's 2, or, you know what I mean? And I guess we could draw it to scale. You know what I mean? If we got 4 millimeters, I don't know. Is that 4 millimeters? Hard to say. But now, if you do have this 2 meters, what's the other number that you need to know? So if you are going to get into this plastic range, maybe the question is, when's it going to break? And so a good estimate is 5%, but it can be up to 30%. You know, probably that would be an extreme high case. You know what I mean? 20%. You know, maybe, but just think 5% and 30%. Those are the two numbers, I think, because if you're out in the back shop, and if you put a little heat to it, you know what I mean, hell yeah, you can easily surpass that. But with cold steel hammering on it, and you don't want it to break, and you're trying to, like, you know, get square stock to, like, you know, wrap around in a circular shape, just so you got something cool. Man, you won't even have cracks or fissures doing that, just with cold, you know what I mean, just cold forming. It's very fascinating. Up to 30%. But, you know, let's say 5% Braco. So what's 5% of 2 meters? No one knows. Or I don't know. You know what I mean? Let's do... You know what I mean? If your bill's $1,000, let's just do 1,000 millimeters first. If your dinner bill for a big party is $1,000 and you need to tip 10%, damn, you know what I mean? That's going to be $100. Okay, but that's 10%. But you're only tipping 5%. Okay, hell yeah. I only have to give. Whoa. I didn't even do that right. $100. Okay, but if it was a 5%, I only have to give $50. You know, it's still a lot. You know what I mean? A 10%, it seems like a lot of money, maybe. Okay, but in our case, we have 200 millimeters. So your bill's $2,000. What's 10%? Hell yeah, that's $200. What's 5%? $100. Okay, so this... I could take this and stretch it 100 millimeters. See how we could just use the strain equations? And we will. So let's write them down, because we have strain is change in length. Let's write them all down. Length is change in length, strain. And then what's the last one? Change in length is strain times length. And what do we want to know? We want to know the change in length. But now, we just said for steel, the max was 0.002, which is 0.2%. And now I'm saying, what? The strain for, like, for deformation? I don't know. I've never even written this, but I would be very careful. Strain for deform is 5%. You know what I mean? And so it's just fascinating. We live in a world of percentages. Who knows why we're so good with percentages, but we hate fractions. You know what I mean? So if I said 5%, what's that as a fraction? Well, that's 5 divided by 100. Like, I don't even know what that is. But now we take that 5 and go 1, 2. And oh, it's like, oh, no duh. Because 0.1 is 10%, 0.5 is 50%, so 0.05 is 5%. Okay, I got it. Back to college level stuff, you know what I mean? So we got 0.05. All right, so we got, but I think that's the reason why these strain equations suck, is because we live in the world of percentages, we hate fractions, and we really hate small numbers. The fact that steel is 0.002, that's why instantly you have to use 1,000 millimeters and then 2 millimeters, because that relationship is visually making sense. You know, even 2 millimeters, I can handle that. I can visualize a 2 millimeter change in length, even though I know that's going to be the max. And I should just say this right now, but I will say it a little bit later, is that you know how we stay in this range, that you don't want to kill people? Well, the magic part about this range is if we put that, what was it, like 15,800 pounds on this, and we stretch it exactly 4 millimeters, if we stop putting that force on and put 0 pounds on, you know what I mean, let go of that force, every single molecule, and it did stretch 4 inches, every single molecule, okay, it not only will go back that whole 4 inches, but every molecule will return to its identical location. It'll be 100% like you didn't stretch the thing. And I think that's a very amazing and bizarre, well, it's just kind of cool phenomenon of science. Basically, you have 2 molecules that are they're not covalent bonds. They're kind of ionic. They're like magnets, you know what I mean? So you have magnets, and you do have space between the molecules, and there's an attraction there. So if you squish them together, you know what I mean? Whoa! And then release, they go back to the same. If you start to stretch those out, where they're still hanging on, you know what I mean? You still haven't killed people, you know what I mean? And then you let go of that force, they go back to that same shape. So that's really cool, and that was part of, you know what I mean, I think material mechanics is you need to be spoon-fed just kind of everything in just small little bites. Like, you want to know the more advanced classes. These are more advanced classes of like, whoa, like how does everything kind of line up, and why do you get more strength? Well, who cares? Don't kill people and stay in that elastic range. But you also, even in the elastic range, no one ever taught me, you know what I mean, the interesting magnetic nature of steel molecules, or definitely metal molecules. They're not covalent, they're ionic, and hopefully I'm not just not saying that right, but anyway, but I think that's a good representation. All right, so hell yeah. So what we're getting at is, like, this was the 4 millimeters stretch. What can we stretch it? And I'm glad we went on that tangent, because yes, we're in the world of, like, when this thing impacts, if this, because we still got to do the problem, holy Toledo, if this thing impacts and the stretch is going to be less than 4 millimeters, and because that's part of the problem statement. What's the maximum elongation? Is it less than 4 millimeters? Probably. If it was a cool problem, it would be bigger. No, I don't know, but whatever. It's just an easy problem. It's less than 4, and it goes back to its original shape. And then calculate the max tensile stress. And this is where everything is just like, oh, calculate the stress. It's like, I could care less about the stress. You know what I mean? We just want to make sure it's less than 58,000. That's our first check on reality. But I think we live in the world of force. You know what I mean? So I want to know what the force is. It can't be 15,800 pounds, because that would elongate at 4 millimeters. And we're thinking this problem, you know, is less than 4 millimeters. And then I guess, you know what I mean? So this is, I guess we got to go on this other little tangent, but this is the stress-strain curve, you know what I mean? This isn't 4 millimeters. This is 4 millimeters divided by 1,000 or 2,000 millimeters, you know what I mean? So right there, that value is going to be 0.002. But you could also, at the same time you do a stress-strain curve, you could do what we're doing and do a curve that's force divided by change in length. You know what I mean? And the only reason why you don't do this is because if you're dealing with steel, everything, every setup with steel that you're pulling in tension or compression will look like this will look like this graph, or I mean, I guess intention. It'll look like this graph. It'll 0.002 will be your max, because because we already chose the area of this bar, and then we have this force that's 15,800. But you could imagine if we had a surface area of this bar to be 1 square inch, we could get up to that 58,000. You know what I mean? So then this value for our problem is going to be 15,800. But if we made the bar 1 square inch, this same height is going to be 58,000 pounds. So this would be a pounds change in length. And this change in length but that's the cool thing actually. For it doesn't matter if this area is 1 square inch or what we have about 1/4 inches squared. This change in length will still be 4 millimeters, because change in length is only a property of change in length is only a property of the actual total length. Because your max strain is 0.002, and that's going to be change in length divided by length. And in both these problems, where we changed the area, we did not change the length. So, but if you change the length, yes, you change this. This obviously changes. If you shorten the bar to 1 millimeter, you know what I mean? This becomes right here 2 millimeters, and that's your top end for your equation, and it goes out plastic. Okay, so sweet. So I think that's a kind of a rundown. And what we wanted to do was find what's the max length that this thing can actually stretch. It was going to be 5%. That's going to be 0.05. 0.05 is the strain deform, so I'm going to go strain D, and that's going to be 0.05. This is the number for strain. You know what I mean? It is synonymous with 5%. And now what's our equations for strain? Right here. This is why you have to have them written and at the ready. Because if I know this, and I still know my length is 2 meters, like, okay, then I can find change in length. You know what I mean? I know both those, I can find that. So let's do it. Change in length is strain deform times length, and that's going to be 0.05 times 2,000 millimeters. I'm only using millimeters because the change in lengths are just very visual if you do that. So times 2,000, and didn't we already do this? Didn't we already say it was going to be 100 millimeters, which is 4 inches? You know what I mean? Visually, that's very close. So, so in one case, you know, we might be able to stretch this up to 4 millimeters before we have issues. And in a lot of applications where you build stuff, you know what I mean, hey, you're into killing people if you go past that for your given length or something. But if it's something that you're okay with stretching until it breaks, just to find out like how far that's going to be. Holy Toledo, you can stretch this 4 inches. You know what I mean? So and 0.1 millimeters is so this would be 1 meter. Right here, this would be a half, 1, 2, 3, 4, 5. So you could stretch it that far. I mean, I guess, you know, obviously this picture is only a couple inches high, but you could stretch it that far compared to just imperceptible. If you're making this to scale, you would not be able to see 4 millimeters on this scale. All right, hell yeah. So let's see where we're at. Okay, this is way cool because you know, with our problem, we're trying to lift something up and then drop it. Here's the extra weight that we're going to put on that bar. So let's say we just rest the weight down there and it's 20 kilograms. You know what I mean? Well, what's that? That's 20 times 2.2 pounds. 2.2 pounds per kilogram. 1 kilogram. You know what I mean? That's the conversion factor, and we got 44 pounds. So holy Toledo. So what would be my strain? You know what I mean? And then so I would get used to writing. We already said that we have strength is force divided by area. Strain is change in length divided by length. And definitely you need to write strength is modulus of elasticity times strain. But you have to have acronyms for these, you know what I mean? So, hey, maybe this is strength allowable, you know what I mean, which is half. I want to allow 29,000 psi. You know what I mean? Hey, strength allowable. Or strength actual. Hey, I want to set up something and I want to know its actual. And that's where it's good to call this stress. It's more just, PS. I would just, if you don't call it strength or stress, call it by its units. You know what I mean? Hey, what's the PSI actual? The pounds, the pressure in pounds per inch, because we know that's the easiest equation. That's like, whoa, we have a force and then we just have a cross-sectional area. That's going to be the PSI between those molecules. And the cool thing is any two molecules can only withstand that PSI in tension or compression before all those things happen. Okay, so we have here, so we can say, hey, strain actual. Now, do we put this label actual on everything? Because let's do strength. Let's say we have strength actual is equal to force actual. Now, would we say area actual? No. You know what I mean? Because we've already chosen the area. We're not going to say area. Area is not a changeable thing in this. So the same thing over here. This equation has a change in length actual because we know we could have a max change in length and due to a max strain. But now when we divide it, the L does not get a subscript. It's just already chosen. And I think that combined with this is one equation is three equations. And the fact that you have a subscript that only goes on two, I think that's the full picture. You know what I mean? So now we can find this actual strain. And if you write it like this, you can also write it in those three different ways. Because we have length is change in length actual. Divided by strain actual, and then change in length actual is equal to strain actual times length. All right, heck yeah. So now because we just said we wanted to put that 44 pounds on this, you know what I mean? So now we want to know what. This is fascinating, because this is why you have to write all three of these equations out. I mean, I do, because if I ever get lost, write all three of these equations out, and then put this one into this, and this one into there. And then you're going to get force over area is modulus of elasticity times change in length divided by length. And what I want to know is if I put 44 pounds on this setup, what is the change in length going to be? What's the elongation? So right here is my full equation. I can say, hey, let's solve for change in length. And this becomes, the L goes upstairs, so it's FL, E goes downstairs, and I would put the E first. It's FL divided by EA. So this is the one that you just want to get used to memorize, because you're going to use this a lot. I don't know if you say, oh, it spells flee, in that direction, but it's just one of the more useful equations that come out of here. Like obviously the second useful one was force. Force is equal to EA divided by L, and even that I would memorize this EA divided by L term and just like, oh yeah, you don't have to memorize it, but then just put change in length out here and just really see how that's synonymous with spring constant change in length. You're like, whoa, those two are identical equations, therefore EA divided by L is the spring constant of whatever your setup is. All right, so we have the change in length is the force. We already said we were going to put 44 pounds on it. We know its length. And we're going to divide by modulus of elasticity, which is just a property. That was the only thing that I didn't explain. When we have this equation, this is just an equation of y is equal to x. You know what I mean? Y is equal to x is just there. But now we're going to say y is equal to mx. You know what I mean? How we say mx plus b, that's equation of a line? Well, this equation always goes through the origin. You know what I mean? So you basically have y is equal to mx. And hey, if this slope is high, hell yeah, you're going to have a steep line. You know what I mean? So even just, I love this aspect of being like, whoa, didn't know I was learning math at the same time. We already said this line is hella steep. And if you're looking at it, it's almost virtually steep compared to, and that was the deal. You know what I mean? We said 4 millimeters compared to 100. So if this was actually drawn to scale, you would have 4 millimeters right here, about 10 there, and you would have 10, 20, 30, 40, 50, and then you'd have double that. So we would be off the page. So this graph, before it breaks, would be off the page, and that's when it would break. So I'm really glad I made that, because when they make these charts, they're only going to put the chart in like, in something, in a space that's going to look like this, where like this thing, for all intents and purposes, is a vertical line, and that goes over. But they're never going to show it like that. You won't be able to see it, so they really exaggerate this part, and this is never to scale. If they're saying it breaks right there, whoa, that's not to scale. This part is totally vertical. And then back to this equation of modulus of elasticity, because this is the y-axis. This is the psi axis. See how calling it psi is just, it takes the edge off. Strength is, I like it, but it's the stress. So you have stress strain diagram, or you could say strength stretch. Cool. Psi, change in length. Divided by total length. Change in length ratio. So cool. So there's just a lot of different ways you can say this. PSI versus change in length ratio. And we want an equation just for this portion. We could care less about the plastic portion because we don't want to kill people. We just want to be right in here. And hopefully we're like right here. Hey, allowable. Like this is stress allowable. Remember that? Maybe we're only going up to like 60% because we want to have that buffer. When, you know what I mean? The building decides to throw a crazy party and not tell the fire department. Okay, you know what I mean? So we have, so it's totally the equation of a line. That's all this is. Now, if the slope was 1, you wouldn't have modulus. If every material just had a slope of 1, that would be a bizarre thing. And, my brother's a math teacher, and he was just like, oh, well, I could, as long as you don't put units on any of this, modulus of elasticity could be 1. You would just have to make up units for, over here, units of pressure, and you would have to make up units for units of ratio of a length term divided by a length term. Cool, but we don't in this equation for a line, and it's super steep, so this is hella big. So that's why this is 29 million. Now, SEA in American units, this is 29 million psi. It's 200. E is 200, usually 200. That's the standard. This problem says 210, but that's obviously it's steel. 200 gigapascals, and again, that's 200 times 10 to the 9. That's just an unregisterable, and that's in pascals. And what's a pascal? That's 1 Newton divided by a meter squared. And again, if you write it like this, you can't go wrong, because I just said a Newton of weight over that Wall Street Journal is 2 sheets of Wall Street Journal. All right, so booyah. So we so that's because you can't just say this equation and just pretend that you know what modulus of elasticity is. You know what I mean? I hate online modules where they're just like, oh yeah, and it's because like they don't know either. You know what I mean? No one knows. But yeah, that's where modulus of elasticity comes from. But if you don't talk about it, you're never going to get like to that next little level where you're just like, the second you do this, I might say just small things that are even wrong. You know what I mean? But then the fact that I say them, it's out in space, and then I actually learn just so much faster from doing that. Cool. So we have this rearranged. We know modulus of elasticity now. It's just a constant. We know the area. We put that into our calculator, and now everything that we're doing is in American units. So our force is 44 pounds. Our length, we got to convert length 2 meters. I need to do factor label on this. I don't know what the conversion factor is. You know what I mean? I've never known. Is it 2 times 2 meters to feet at least? 2 meters times 2 times 3.3? Is that what it is? Are we going to get something pretty close to 6.6? But we need it in inches anyway. You know what I mean? This is in PSI. You know what I mean? This is pounds per inch squared. Area has to be an inch squared. Those can cancel. You know what I mean? And then you have force in pounds, and then your length. I guess, you know, if you're a math whiz, you can realize that this length stands alone. So it actually, oh, this is gonna trip me out, and I think we should really do this because it's irrelevant of yeah, it's irrelevant because psi, pounds per inch, cancels that, and because change in length is a unitless ratio. Oh, this is going to be so cool. So I'm going to put 2,000 millimeters here just because I know that I can do that, and you know, I mean, we can maybe double check on reality, but obviously it'll work out, and I don't have to do my conversion factor. I've never liked converting meters to feet or inches. Okay, so we have 2,000 millimeters divided by 29 million pounds per inch squared. That's in psi. And then in area, you know, I mean, this again, area is pi d squared divided by 4. But we have, but even here, you got to get this in meters. You know, I mean, this is 0.015 meters if you're going to use, if you're going to get the area in, even if you're working in, because Pascal is going to be a Newton meter squared, so then you want to get your area in meters squared. That's the only way those meters are going to cancel. And then I kind of just forgot our area is in inches squared anyway. We already converted that. So we're going to have 0.2739 inches squared. And hell yeah, everything cancels, and we can find our change in length in millimeters. Cool, so let's do that. So we got 44 times 2,000. I'm going to get a little techie. I don't want to write all these parentheses. We're just going to divide by 29. 1, 2, 3, 1, 2, 3, that's a million. And then we just divide again to get this one. You know, instead of putting a parentheses around all that. It's just a fun little calculator trick that I've been digging. And it just makes my life just so much easier. And anyway, this is alpha A anyway. Cool. Alright, so there you go. So we have a change in length of 0.01 millimeter by putting 44 pounds on it. And did you expect that? You know what I mean? Because there is a ratio here. We said if you put 58,000 pounds, you're going to get 4 millimeters. You know what I mean? So let's put 29,000 pounds. You're going to get 2 millimeters. Let's put 29,000 divided by 2. Let's put 14,500 pounds. You're going to get 1 millimeter change in length. So yeah, I didn't realize that I was using American units, but always saying my change in length in millimeters, because you can, because it's a unitless thing. You know what I mean? Because it's just a ratio. It's your 0.002 is a ratio of your change in length divided by your total length. So these can be any units you want them to be in, and so that's kind of fascinating. All right, but I would probably have everything in inches. You know what I mean? If you're gonna have pounds and inches, I would have my length in inches and my change in length in inches, just not to make any errors. But what I'm getting at is like, well, what? So then what gives? If I have 44 pounds, how do I figure this out? You know what I mean? And like I've never liked fractional ratios. Even just writing it like this is just like making my but you could do this. Sometimes I like to do this. So now I don't know, but you do, like anytime I do this where you're like, hey, these things are equal, do not write them in a straight line. Stack them. You know what I mean? So you can say 58,000 pounds is 4 millimeters. You know, we do this a lot in physics and science. You're just like, hey, this is, when I get 58,000, this is equaling 4 millimeters. My setup, you know, those two are equals. So what am I saying? Well, I just have 44 pounds, and I want to know 44 pounds. And I want to know how many millimeters. But if I did this, 1 divided by 44, pounds would cancel, but now I would have divided by millimeters, you know what I mean? So using the factor label method, so now what we're going to do is we're going to use my trick, units are the equation. We have pounds per meter, and we can also write this as meters per pounds just by flipping it upside down. And then we have pounds. So what do we do to these two things to get our length in meters or millimeters, you know what I mean? Obviously, we just multiplied these two things. But let's say we didn't realize that we could flip this upside down. We have pounds per meter, and I want to get pounds. Like this is a good skill to have that comes up a lot. That's just like, my brain can't handle this. You know what I mean? Just another little thing to do. I want meters up top. And like, what do I do? Because this happens with like meters per second and meters. If I have, let's do that, meters per second and meters. If I know my velocity and I know my distance, so I know I'm going to travel 60 miles per hour, and I know the next town is 60, I'm just going to say 30 miles away. What do I do to these two things to get time? Well, to get time to pop up to the top, I do meters divided by meters per second. Meters cancel, times pops upstairs. And in this case, it would be 30 miles divided by 60 miles an hour, and that gives me that classic half hour. Okay, sweet. So I'm going to take, and this is the 44 pounds. I'm going to take 44 pounds and divide it by pounds per meter. You know what I mean? And so we got 44 divided by 58,000 divided by 4 millimeters. Cool. And so we get 0.003 millimeters. Now why are we off? I gotta pause the video. Oh, hell yeah. So that was cool. I caught my air real fast. Because the max strength of this is not 58. I should say. Holy Toledo! I got to pause it again. No, we're good. But yeah. So this is just pounds. It's not in psi. What we say if we have a 1 inch by 1 inch chunk of steel, we can put, it's got an area of 1 inch, so we can put 58,000 pounds per square inch because that's the breaking strength of steel. We don't have that. We have, so our force, so here's the equation. You can write this 3 different ways. We want force is equal to the strength times area. So if we want force, A's got to go upstairs. And then so we have that 58,000 pounds per inch squared times our area, and that's like 0.27. So we go 58,000 alpha A, and yeah, we only have that 15,886 pounds. So yeah, so we can do this representation. We just have to put 15,886 right here. So I'm going to store that as alpha F for our force, and now we're going to go 44 divided by alpha F divided by 4 millimeters. And booyah, now we're cooking. So I apologize for that error, but actually I love errors because we're going to make them, and it's just fascinating if you can find them fast. And I think I've been doing a pretty good job of doing that, finding them fast. Alright, hell yeah. So what we're going to do is end this video, you know what I mean? Because this was an intro to material mechanics, you know what I mean? Even though we have a problem that involves impact loading, we kind of, I mean, this is the first thing you want to do with any material mechanics problem, is just like, well, you still have something made out of metal, it's got an area, it has a strength max because it's steel. And we just found out that could stretch 4 millimeters, or it could, or you could put a pounds of 15,886 pounds on it. And we'll leave it with that because I don't think people have this like solid understanding of material mechanics of like, oh, something, I can break something in 2 different ways. I can register a force on it, you know what I mean, of 15,886 pounds, or I can visually see its change in length. So I can put a force on it, but then visually see its change in length. And if that gets past 4 millimeters, I know I'm at that max. You know what I mean? So so that's pretty cool. And obviously, if we just rest this 20 kilograms on it, it doesn't stretch it at all. You know what I mean? We get nowhere close to 4 millimeters. We got 44 pounds compared to 15,800. So now we get into the impact side of things. Like, why, when we drop this, can you generate 15,000 pounds of force? And it's just fascinating because and the short answer is F equals ma. And I really like to explain that in terms of F equals ma, because because what we're going to have is we're going to drop this from some height. You're going to have a velocity. I mean, because of gravity, you have the acceleration. You know, on it is 10 meters per second squared. So every second this is in free fall, it's going to have a speed of 10 meters per second. That's why I initially did the problem with 5 meters, because the kinematic equations come out that if you drop something, and this is very fascinating. We'll obviously do it in 2 parts. We're going to get some fresh sheets of paper, but just to not leave you hanging with a cliffhanger, we'll have an initial velocity up here before we drop it. And in my problem, we're going to drop it from 5 meters. And why 5 meters? Well, because I know that the time when I drop it till the time it hits is going to be 1 second. We're going to talk about why I know that. But if that's the case, gravity says if anything's falling due to gravity, it's going to change in speed by 10 meters per second every second. So it's going to have a velocity of 10 meters per second. And yes, now we're in meters per second. You know, we're not in American units. And if something starts at a 0, ends at 10, it has an average velocity of 5 meters per second. And we just said it dropped for a second. Sweet. So it dropped 5 meters. That's why if you have a drop of 5 meters, you're going to get a speed of 10 meters per second. You know what I mean? So that's the kinematic equations, but you do something simple like that, and now you understand the kinematic equations from just like this, oh, aha moment. You know what I mean? Just like we figured out, hey, the strength of this is 58,000 pounds per square inch. We don't have a 1 inch of it, so we know that the strength of this can take 15,886 pounds. You know what I mean? And let's get some more labels on this, because obviously we said we could call this strength max. That's going to be force max. And I think we already did that, but I don't think I actually, strength actual, force actual. But yeah, strength max 58,000 is associated with the force max because we already chose the area of our, you know what I mean, the cross-sectional area of our bar. Cool, cool. So with the impact part, cool. Now we have something that's coming in at 10 meters per second. Now, it's an F equals ma perspective that the only thing, if you have a mass and some sort of velocity, the only thing that can change its velocity is a force. You know what I mean? So we've identified a mass, and we need to change its velocity. That's what we want. So we have this mass times change in velocity is going to require a force. There's no other way about it. It's definitionally F equals ma. And so where can we like hold that back and slow this thing down? Well, we actually use the spring of this to do that. But the thing about a spring that you have to know, and going back to our original springs, is at full length, when you're just pushing just a little bit on it, it's going to change in length just a little bit, but that requires 0 newtons. You know what I mean? The first little bit of change in length, just think it requires 0 newtons. And then you push it in and you get a max change in length. And obviously that's the spring constant again. You know what I mean? The spring constant is that in meters, and I want to push it in 0.5 meters. So cool. It looks like, or no, 0.1. I'm sorry, 0.1. So in this case, how the hell, whoa. How the hell did we get 88.8 newtons? And and we were pushing in 0.1 meters and get that, like, okay, we got to hold up on that, because that could be a huge error. I mean, so just because, yeah, I think the spring constant is kind of confusing, you know what I mean? So let's say this was my spring constant. I think it's totally wrong. 1,776 newtons. And I'm pushing 88.8 newtons. Like, even just that, visually I can see that we ain't going, well, I don't know. Well, let's see. So, it's going to require 177.6 newtons to go a meter. No, we might be right, because I only have 88, and it's 88.8 divided by 1. So that's the proportion. So I have 0.05 of this, and yeah, that's the distance that I'm moving. And oh yeah, this was 4 inches, and I'm moving it 2 inches. So yeah, holy Toledo, it just didn't look right. You know what I mean? But if I want, yeah, I'm only moving it 0.05. I'm moving it a 20th, 1/20th. So 1,776 times 1/20th, which is just divided by 20, is 88.8. Yeah. So I'm glad I didn't mess up that. But what were we talking about? We were talking about how a spring, if you just put like almost no force on it, that first change in length requires almost no force. But then you get up to a max force, and heck yeah, that's going to be your max change in length. So if you do change the length of a spring, it requires you to hold that force against the spring constantly. You know what I mean? And so just think that's the max. This is max, and then you know that you do have a minimum force initial. F naught was 0 newtons, and it's very fascinating. But it's just like how, hey, velocity is 0 meters per second, and then we get up to a velocity of 10, and the average velocity was useful to find change in time. Now it's totally different. We're going to have a speed of 10 meters per second, and I mean, what we're going to do, I guess, back to the F equals ma, we need a force to slow that down. If we do have a force, we need to change this velocity by 10 meters per second. You know what I mean? That's going to be our change in velocity. We don't know how long we're going to do it, because we have to do it in a very short amount of time. If we had another 5 meters to do it, that's the cool thing about these problems. If you have another 5 meters to do it, then, yeah, it's just going to take, like if it gets up to the speed and then you kind of slow it down, it's going to, whatever force gravity was on this, the force of gravity is what's causing this mass to change its velocity. So with F equals ma, sometimes it gets confusing between this side and that side. Okay, so hell yeah. So then if it gets up to some sort of velocity and I want to change that velocity kind of in that same distance, it's going to require the same upward force as gravity. So what was the force of gravity, on this? And it's going to be the mass. That's going to be 20 kilograms times 10 meters per second squared. That's how many newtons? It's going to be 200 newtons. 200 divided by... 200 is 200 divided by 4.44 is going to be 45 pounds. Yeah, we already figured that. 44 pounds. So you would have to put a force of 44 pounds constantly on that thing to slow it down. But we don't have something to put 44, but we do have this hella steel spring that at its max can put a force of 15,000 pounds. Like, we're going to have way more force, than needed, but we can only apply that force in 4 millimeters. So that's the trip. That's the trip that we're going to explore in this next part of impact loading. So that was kind of the introduction of impact loading. It requires a force, and we definitely need the force average. The force average is going to, because the second this thing hits, there's going to be no force, to elongate this just a little bit. It's going to require no force. But then once it does, once this thing does come to a stop, that's going to be this spring is going to be fully elongated, and that is going to generate that. Then that means that this mass is putting a force max, and that force max might be 15,000. And if that's the case, we have an elongation of 4 millimeters. But that's where I like to use F equals ma, but a lot of people just use energy. Obviously, energy is the simpler way to go, but you probably don't know what's happening. Because why did I say force max? Or why did I say force average for the spring, which was force, or if you do find the force max in the spring, the force average over that distance, just like driving, the force average is going to be the force max divided by 2. And that gets into, I always draw this diagram. If you're going 0 to 60 miles per hour in a half an hour, your average speed is 30. And only from this average speed is it just totally obvious how far you went. You went 30 miles per hour in a half hour. Well, it looks like, and maybe I've messed this up a few times, but I usually put 1 hour here, went 30 miles. But hell, we're going to go 15 miles in this example. And the same thing is going to be true for, the force average on this spring is going to be the max divided by 2. It's going to be the force average. And we're going to use that in our energy equation because energy is basically force average times that distance, and that's the change in length again. Cool. And then we have an equation for change in length. But we want to kind of go a slow roll through that so nothing gets missed. So this is part 1. Kind of intro to material mechanics, where then you can see how you can take a problem and you're like, oh, damn it. Now we have to involve F equals ma. A lot of material mechanics properties you don't, because you just have static forces. You know how much something weighs. You know that gravity, there's a force of gravity, but that's just usually, a constant. Given a mass, because you're somewhere near the surface of the earth, that distance isn't changing, and nothing's in motion. Usually everything is just resting upon resting upon resting on other things. Okay, but this is going to require some dynamics, and then it's going to generate a force. Once that force gets generated, that max force is going to determine the max elongation. Now, obviously that's just the maximum. When this thing stops, hell yeah, it's at a max change in length. But after that, after that thing stops, there is, this is fascinating, because the force that's requiring to change that velocity is going to be the force of the spring. But once this mass has no velocity, once it stops, that velocity. The velocity of that mass is 0 meters per second, and you still have that mass. But you just lengthened a spring. And then guess what? Now that spring is actually going to put that force back onto the mass. So it's going to go down, stretch out, stop, and then go back up, and then start to oscillate just within. If it stretches 4 millimeters, it's going to go the other direction, and it can possibly go the other direction in compression 4 millimeters, and then you'll have this oscillating back before 4 millimeters before it dampens out just due to frictional forces. But that's kind of the full explanation. We're not even going to talk about that probably in our setup of doing this problem for impact loading. So hell yeah. So thanks for joining me for this one, intro to material mechanics, and how you can be like, hell yeah, now we can do a problem on impact loading.